Hello. I will start with two Section A questions from the May 2018 paper. So in the coming exam, there will be no distinction between Section A with questions worth 10 marks and Section B with questions worth 20 marks. So there will be a total of 5 questions, each of which is worth 20 marks, so like all the Section B questions. But I'll still try and solve a couple of Section A questions because, 10 plus 10 is 20. So one of the questions which is worth 20 marks could be the union of two separate questions. So the first one that we'll deal with is this question here, which is about dispersion relations and dispersion and dissipation. And we have this equation here. So let's start first by computing the dispersion relation for that equation. So as usual, we sub in u of x and t equal to a plane wave e to the I kx minus omega t. We substitute it in the equation here to find omega as a function of k. So when I substitute, every time we take a derivative of the exponential, we get the exponential times the derivative of the exponent. So each of the 4 terms will have an exponential factor that I will not write. I will just write the derivatives of the exponent. So ut means that we take the derivative with respect to time. So we get minus I omega. Then I have ux, that's derivative with respect to x of the exponential, gives us plus ik. Then we have minus a times twice the derivative with respect to x, so that's ik squared. So we get plus ak squared. And finally, we have minus b times the third derivative with respect to x, so that's ik cubed, so we get plus ib k cubed equal to 0. So now we can solve for omega, which will be a function of k, and we find that it's equal to k plus b k cubed minus I a k squared. Okay, so this is the dispersion relation. So next we can move on to part A. So in part A, we're asked for which values of A and B is there dissipation, and for which of these values is the dissipation physical. And we're reminded of the fact that the wave has physical dissipation if the amplitude of the wave decreases with time. So, dissipation occurs when the dispersion relation is complex. So in particular, let me write this down. So dissipation would be complex omega of k. And so since the parameters a and b are real, this will occur when a here is non-zero, so that omega has an imaginary part. On the other hand, dissipation is physical if the wave, the amplitude of the wave decreases with time. And since in the exponent we get I minus I omega times t here, we see that for physical dissipation, we need a negative imaginary part of omega. So for physical dissipation, we need imaginary part of omega of k less than 0. And that's the case when a is positive, since the imaginary part of omega is minus ia k squared, and k squared is positive. Okay, just as a check, let's check that when a is positive, the amplitude of the wave decreases with time. So when a is 0, we get that the plane wave looks like u of x and t, that's proportional. We'll only write the part that depends on time. We get e to the minus I omega times t, and therefore we get e to the minus I times the imaginary part of omega of k times t. So that will be the time dependence of the amplitude, which is exponential of imaginary part of omega k times t, which in our case it's exponential of minus a k squared t, which indeed goes to 0 as t goes to infinity, since a is positive and k squared is positive. So that answers part A of the question. So in part B, instead, we need to compute the phase and group velocities and discuss for which values of the parameter B there is this dispersion. So in part B, we first need to set A equal to 0, in which case the dispersion relation becomes omega is equal to k plus b k cubed. And then we need to compute the phase and group velocities, c of k and cg of k. Let's start by doing that. So let's start with the phase velocity. C of k, which I remind you is the velocity at which wave crests move, and this is equal to omega divided by k, so that's equal to 1 plus b k squared. On the other hand, the group velocity Cg of k, which is the velocity at which wave packets move, is just the first derivative of omega as a function of k, so we get 1 plus 3bk squared. Okay, and notice that in this case, there is a non-trivial dispersion relation, and the phase velocity and group velocity are different. So finally, we need to discuss for which values of B, the remaining parameter, there is dispersion. And so dispersion, I remind you, occurs when plane waves with different wave numbers move at different speeds. And so here, clearly when B is different from 0, there is a dependence of the velocity on K. So here dispersion occurs for B different from 0, because in that case, plane waves with different wave numbers move at different speeds, in particular different phase velocities. So now we move on to exercise 2, which is about traveling wave solutions. And we have here an equation which seems to be a generalization of the KdV equation, where the nonlinear term goes like u to the n ux, where n is a positive integer. And we have boundary conditions that u, ux, and uxx go to 0 as x go to infinity, plus or minus infinity. And so we're told that we can use this indefinite integral here, and we can assume that u is between 0 and b over 2, 1 to the power 1 over n. So as usual here, so we look for a traveling wave solution. So now we substitute in the equation u of x and t in the form of a single function f of a single variable xi, which is equal to x minus vt, where v is the velocity of this traveling wave. Okay, so let's substitute this into the equation here. So we get minus vf prime from the first term by using the chain rule. Then we get plus n plus 1, n plus 2 f to the n f prime plus f triple prime equal to 0. Okay, so now we'll start integrating, and we'll use the boundary conditions at u and its first two special derivatives go to 0 at special infinity. So let's first integrate over xi once. So we get minus vf plus n plus 2 f to the n plus 1 plus f, sorry, double prime equal to a constant a. But then we can fix the constant by looking at the boundary conditions at infinity, and at infinity u and its first two derivatives go to 0, so f and its first two derivatives go to 0, so a will be equal to 0 by the boundary conditions. Okay, so now to integrate once more, I will first multiply by f prime and then integrate. So let's first multiply by f prime. So I get minus v f f prime plus n plus 2 f to the n plus 1 f prime plus f prime f double prime is equal to 0. And now we can integrate over xi again. So the first term gives me minus v over 2 f squared. The second term gives f to the power n plus 2. And the third term gives 1/2 f prime squared. Now this is equal to another constant, integration constant b, which once again we can fix by looking at the boundary conditions. And because the boundary conditions set the field and its derivatives to 0, b is also equal to 0. So now I can solve for f prime squared. And we get that f prime squared is equal to f squared v minus 2 f to the n, if I factor out an overall power of f squared. And now I can take the square root, so f prime is equal to plus or minus f. And then let me factor out also v, so now I get square root of v, and then I get root of 1 minus 2 over v f to the n. Okay, so now we want to integrate this equation so we can separate variables. So we get df over f root of 1 minus 2 over vf to the n is equal to plus or minus root v d xi, which we want to integrate. So on the right-hand side, we just get plus or minus root v times xi minus an integration constant, let me call it x0. And on the left-hand side, we get this integral of f. So now this integral is similar to the integral here that we're given, but it's not quite written in the same form. So to get it in the same form, let us set y equal to 2 over v f to the n. So in which case we get that the derivative of the logarithm of y, so it's dy over y, is, so if I take the logarithm, I get that log y is proportional to log of f to the n, which is n log of f plus a constant. So I get that this is equal to n times the derivative of the logarithm of f, which is df over f. Okay, so now essentially we can use this to rewrite df over f. That's equal to 1 over n dy over y, and then the square root becomes square root of 1 minus y. So we get precisely the type of integral that we're given if I call the dumb integration variable y instead of x. So this is equal to plus or minus square root of v times xi minus x naught. So if we use the given integral, we obtain on the left-hand side minus 2 over n arctange of root of 1 minus y, which was equal to 2 over vf to the n. And on the right-hand side, plus or minus square root of v xi minus x naught. Okay, so now I can take the n over 2 to the right-hand side, and I can invert the arctange, and then I can square. So I get 1 minus 2 over vf to the n is equal to hyperbolic tangent squared, because I invert the square root of n root v over 2 xi minus x naught. And I didn't worry about the plus or minus sign, because when I take the square of the hyperbolic tangent, that's an even function. Okay, so all right, we're almost done. Now I can just solve for f. So I get f of xi is equal to v over 2 times 1 minus hyperbolic tangent square of n root v over 2 xi minus x naught, all raised to the power 1 over n. So if I write everything in terms of u, which is a function of x and t, I get that u. Oh, I can also use the fact that 1 minus tangent squared is 1 over cosh square, which is hyperbolic secant square. So let me do that. V over 2 times hyperbolic secant squared of n root v over 2 xi minus x naught. So if you didn't do this in the exam, I think that would be fine with me. But anyway, okay. So in terms of x and t, we get that u as a function of x and t is given by v over 2 hyperbolic secant squared of n root v over 2 times xi, which was x minus vt minus x0, all raised to the power 1 over n. So this is the traveling wave solution that we were after.